In this lesson, we have several objectives. Our objectives are to classify triangles according to the sides and angles, to state and apply the theorem and the corollaries about the sum of the measures of the angles of a triangle, as well as to state and apply the theorem about the measure of an exterior angle of a triangle. So beginning our conversation of triangles, we need to first define what is a triangle. Well, a triangle is a shape where we have three segments joining three non-collinear points. And I think most people are familiar with what a triangle is, but it looks like this right here. We have three segments, and they're all joined by various points, by three non-collinear points. And now there are different parts of the triangle we need to discuss. We have first what is called the vertex. The vertex are the 3 points, so A, B, and C. So right here, this point is a vertex, this point, and this point are all different vertices. Vertices is plural for vertex. And then we have the sides. So you're looking at segment AB, and then you have segment BC, and then segment AC. We have 3 different sides that make up the triangle. We also have 3 different angles that are created. We have angles ABC, this angle right here, angle BCA, this angle, and then angle BAC, which is this angle. Now we also need to know how to name triangles. So when we're naming triangles, we need to use the 3 letters that are given to us. So it does not matter the order in which we use the letters. So it could be like ABC, you can use BCA, it could be CAB, CBA, ACB, BAC. It can be any of those varieties. Now it doesn't matter with triangles, but later we'll learn with other shapes the order does matter in the sense that once we pick a letter to start with, we need to make sure that we go in the same direction. So in this example, if we started with A and we started going to the next point, point C, then the next point after that we need to write is going to be the next point over, which would be point B. So in this case, it doesn't make a difference, but with other shapes, as we'll discuss later, it will make a difference in the order. Next, we have a theorem that says that the sum of the angles of a triangle is 180 degrees. So for example, if measure of angle A is 60, measure of angle B is 80, measure of angle C is 40, when you add them all together, we will always get 180 degrees. So it doesn't have to be 60, 80, 40, as long as the measures add up to 180. Now with triangles, we have different ways to categorize triangles. We can categorize by length, and we can categorize by angle measure. So we'll first begin by discussing the angle measure way of categorizing. So based on angles, we have what we call an acute triangle. An acute triangle has 3 acute angles. So for example, if you look at this triangle to the right, notice every angle is less than 90 degrees. Every angle is acute. So that would be an acute triangle. Next, we have an obtuse triangle where we have 1 obtuse angle, such as this picture over here. We see that this angle is definitely bigger than 90 degrees. So because we have an obtuse angle, this triangle we would consider to be obtuse. Next, we have a right triangle, which is a triangle with 1 right angle. So for example, we have a triangle over here where a 90-degree angle is in the bottom left corner. So this would be a right triangle. Next, we have what is called an equiangular triangle. You see the prefix equa, and equa looks like equals, right? So what this means is that we have a triangle with equal angles, and that is our definition. So for example, right here would be an equiangular triangle, where every angle is going to have the same measure. And so a side note with this, if we know that the angle measures of a triangle add up to 180 degrees, and we know that these 3 angles are the same, well then each angle can be found by simply dividing by 3. Every angle must be 60 degrees, in order for them all to be the same measure and add up to 180 degrees. So each angle is 60 degrees. Now we can categorize triangles by side length as well. So the first type of triangle we have is called a scalene triangle, where no sides are congruent. So something along these lines, where maybe this left side is 12 inches, the bottom maybe is 10 inches, and then the right side is maybe 8 inches. Every side length is different, so that would be considered scalene. The next one is an isosceles triangle, where we have at least two sides that are congruent. So here we see that the left side and the right side are congruent, and maybe the bottom side, but it probably is not. But the left two sides, the left side and right side, are congruent. Maybe it could be 10 inches and 10 inches, something where they have the same measure. And it can also include triangles that have three sides that are congruent as well. So if every side were the same measure, that would also be considered isosceles. But if it has all three sides that are equal, there's a special name we can give in addition to being isosceles, and that is the name equilateral. An equilateral triangle is a triangle where all the sides are congruent or equal. So for example, right here, we see that every side is congruent. So because of that, we have an equilateral triangle. By the way, notice I'm putting these little lines through the sides. In a picture, if you don't know if the sides are congruent, if you see one line through it, the two sides or three sides or however many sides that have the one line through it are going to be congruent. And there are times when you might see a side with, two lines. So if this were your picture, that means that the two segments with the two lines through it are congruent, and this third side with just one line is not congruent to the other two. And by the way, an equilateral triangle would also be equiangular, meaning every angle is the same. Now we're going to switch gears and talk about different aspects of triangles. And before we do that, there's a term that you need to know. And that term is the word corollary. A corollary, by definition, is a statement that can be proved easily by applying a theorem. So something that just logically falls into place without really needing to prove the statement. So for example, one of the corollaries that we have says if two angles of one triangle are congruent to two angles of another triangle, then the third angles are going to be congruent as well. So for example, here we have two triangles and we have two angles that are congruent. The 80-degree angles are congruent and the 60-degree angles are congruent. Well then, with this picture, we can conclude that angle C and angle F must also be congruent, because we know a triangle has 180 degrees total, and right now we have used up 80 degrees plus 60 degrees to give me 140. So the remaining degrees we have left would be 40 degrees for angle C. And notice same thing is true over here with the other triangle. Angle F must also be 40 degrees for the same reason. So this is a corollary because it does not really need to be proven. It kind of falls into place knowing the fact that a triangle has 180 degrees total. A second corollary says that in a triangle, there can be at most one right angle or obtuse angle. And this makes sense because if you're to try to draw a picture of a triangle with more than one right angle or one obtuse angle, you'll find very quickly that it cannot be done. Where here, if you try to draw one right angle, we have something like this. So here's one right angle. But then if we try to draw another right angle for the triangle, we would have another angle up here. That is a right angle. And notice these top and bottom lines would never intersect to create a triangle. The only way for them to intersect would be to draw a fourth line down something like this. Okay, so we cannot create a triangle with more than one right angle because the segments would not connect. And same logic with the obtuse angle. If we try to draw a triangle with one obtuse angle, we'd have something like this. But then drawing with another obtuse angle, maybe over here, notice we're going to get something like this, and there's no way that these two segments on the left and the right will ever intersect unless we draw a fourth line to connect them. So this corollary does not need to be proven because it's kind of self-evident if you just try to draw the picture. Another corollary says that the acute angles of a right triangle are complementary. So for example, if we have a right triangle, then we know the triangle has 180 degrees total. If this is your right angle, then we have 90 degrees being used up, which leaves me with 90 degrees to split between angle A and C. So we know that angle A plus angle C needs to add up to be 90 to fill in that void of 90 degrees that is missing. So we know that angle A plus angle C would have to be 90 to give you 180, and that by definition would make angle A and C complementary. Because complementary means that we have two angles that add up to be 90 degrees. Now we're going to switch gears one last time to discuss the last topic for this lesson. And as we discuss this last topic, we need to first begin by giving a definition. And the definition is of the word auxiliary line. An auxiliary line is a line, or I guess it could be a ray or a segment, added to a diagram to help in a proof. So if there's a ray or segment, it would be an auxiliary ray or an auxiliary segment. And so here in this next picture, we see that we have a triangle drawn, triangle EFD. But then we extended the segment ED to get DG over here. So DG would be an auxiliary line, which is something being added to the picture in order to help prove or show something. And with this picture that we have drawn, we have different names we give to the different parts of this picture. So with this specific drawing, this angle outside of the triangle, right here, angle FDG, is what we call an exterior angle because it is on the outside of the triangle. So not EDG, but FDG. And then also we have what we call remote interior angles. Now the word remote means isolated, and interior means inside. So we have isolated interior angles. Well, isolated from what? What we mean is isolated from this exterior angle. So which angles are on the inside and are not next to that exterior angle? Well, that's going to be angle E over here and then angle F over here. So angle E and F would be what we call remote interior angles. So we use three letters probably to name them. It'd be FED to have this angle, and then EFD to have this angle up here. Now using this picture, we're going to now put in some angle measures. So let's say this exterior angle is 100 degrees, and FED is 65 degrees, and EFD is 35 degrees. What can we conclude based off this picture about the measures of the exterior angle and the remote interior angles? Well, notice if we take the remote interior angles of 35 and 65 degrees and add them together, that's going to equal 100 degrees. And we'll find that that is always going to be true, where the remote interior angles will add up to be the same measure as the exterior angle. And if we think about it logically with this picture, if this angle is 100 degrees, then angle FED we know would have to be 80 degrees because it's going to add up together to give me this line, which a line has 180 degrees. So if this angle is 80 degrees, we know that the other two angles over here would have to add up to give me 180 as well, because all three angles together would give me 180. So we know that angle EFD and FED would have to add with this 80 degree angle to give me 180. To make that happen, the two angles would have to be 100 degrees, because 100 plus 80 would give you 180. And here is an example where we are trying to find the value of x based off what we just stated. Well, x is exterior angle, and then 35 and 70 are remote interior angles. And we just stated that the remote interior angles will add up to be the same as the exterior angle. So if we add 70 plus 35, we get 105 degrees. And that's going to be the same or equal to x, the exterior angle. So x would have to be 105 degrees. And if for some reason you forget this property, then you can just think through logically that we have 70 plus 35 gives me 105, and then a triangle has 180 degrees total. So 105 plus something gives me 180. Well, this angle would have to be 75 to add up to be 180. And then angle x plus 75 would also be 180 because that creates a line. So 75 plus that x would be 180. So x would have to be 105 as well. So if you forget the property, you can just think through logically to find the same solution. And that concludes our lesson for today. We will see you next time.